All right, welcome to our final topic in the grade 11 course. We're looking at woodwinds and stringed instruments, and we're going to go through and just talk about some of the general properties and mechanics on how they work. So what's the goal? I can explain how various wind and stringed instruments work using concepts discussed in the unit using proper terminology. So as we go through here, let's start with our open-ended instrument. So just a quick recall from the previous lesson. We talked about the formula for an open-ended air column, and we have n over 2 lambda. And we said that the nodal points have to either be here or here when it comes to an open-ended column. So you're going to have either a wave that looks like that. So that's our fundamental wave right there. Or it could be reflected in terms of oscillation. So it could be there as well. So there is our open-ended air column. Closed-end air column, very similar. How do you calculate the length? 2n minus 1 over 4, and you're multiplying by lambda. The nodal point has to be here for a resonant frequency, so you end up with a 3/4 wavelength, looks like that. Or when it reflects or oscillates, could look like that. Okay. So keep in mind, what does n represent in both of these cases? So the one thing I want to add then is, or clarify, or make sure everyone's comfortable with, is n is our number of nodal points, or at least it was with the previous lesson. And it also could mean or represent the number of resonant length. So the third, fourth, fifth resonant length. All right, so when you're going through and doing some of the homework, resonant length, they could use either terminology to give you the value of n in the question. All right, so if velocity remains constant, so we're going to keep velocity constant, all right, we're going to apply the universal wave equation, so v equals f lambda. If velocity remains constant here, then what happens to everything else? Well, we have two options for frequency. Frequency can either go up or frequency can go down. So I'm going to work across here. So I'm going to go with blue for frequency going up. If we increase our frequency, and we're looking at this equation, if I make this number larger, if velocity can't change, this number is going to have to decrease. So my wavelength will decrease in length. It'll get shorter. What happens to the pitch of the instrument? Well, if you increase your frequency, think back to when we talked about the Doppler effect. If the waves are hitting you at a higher rate, the pitch will increase. So your pitch increases. So the connection, or what we're looking at here, is if I want to increase my pitch, and that's what a musician wants to do when they're changing or playing their music, they need to increase their frequency. How do you increase your frequency? Well, you will, with a woodwind, physically change the wavelength of your chamber. So you'd shorten the chamber in order to increase frequency, which would increase pitch. So they're all interrelated. If the frequency wants to, if we drop our frequency, make that frequency smaller, that means that lambda would have to get greater. If you drop your frequency, so this is when the vehicle goes by and it's still honking the horn, then the pitch sounds like it is dropped. And here we are with this circular argument again. If a musician wants to drop their pitch, they have to decrease the frequency. How do they decrease frequency? They increase their wavelength on the wind instrument. So they're all interconnected, and that's what we're looking for in general when we're talking about that. So moving on to the next slide here, with air columns, we have to keep the frequency constant. So for people that play instruments, you know that you try to blow, for the most part, kind of with equal pressure, equal force, whatever the proper terminology is. So what that means then is that we can, with your fingering on the instrument, you can either increase the length of the column or decrease the length of the air column. If you increase the length of the air column, then you are decreasing your pitch, as we talked about already on the previous slide. If you shorten the length of your instrument, you are increasing your pitch. So there is your relationship between the two. So let me talk about a couple of instruments in particular. The first one I'm going to talk about is the trombone. So the trombone is a unique instrument, and the one thing I like about doing the video lesson here is I don't have you sitting there mocking my my beautiful drawings. So this is going to be my attempt at the trombone. For people that don't know what it looks like, then you won't know the difference. But I'm just going to draw my trombone like this. So, and I know I have people in the cloud. You're laughing right now. Guess what? I can't hear you. It doesn't hurt my feelings. Okay, so with the trombone, you blow into it with the standard pressure or whatever, and you create your standing wave. So I'm just going to bounce a wave around inside the tube. Yes, I know it doesn't look perfect, but guess what? It is for me. All right, so there is our standing wave. What the trombone, one of the unique properties of it is that it will have kind of an overlapping tube here, for those that don't know, and it's called a slider. Okay, so if you want to change the trombone's frequency, or the pitch of the trombone, you simply change the length of the slider. Okay, so here, for example, I'm going to say that the tube has a length of L1. All right, so a person's playing a particular note. They then want to play a different note. So now I'm going to attempt to redraw. And this time they slide it out. So now the trombone now looks like that. And again, there are people laughing at me. And you know what? That's fine. Doesn't bother me. So there my trombone has been extended out. And it has gotten fatter, obviously, because that's what happens when you extend it out. No, not really. All right, so there we go. So now what's happened is that L1 has now become L2. So I've greatly increased the length of the tube. If I've increased the length of my air chamber or the column, then I have decreased my pitch. So now I'm playing a lower note, so to speak. All right, so the trombone, and I'm going to make a note of it here. So first thing, it has the greatest range in pitch, as the length has, and I'm going to put this in quotes, no restrictions. Obviously, there are obviously restrictions in the sense that it can only go so short, it can only go so long. But you can increase the increments by a centimeter, so i.e. Increase by 1 centimeter, increase it by 10 centimeters, or you can increase it by 1 millimeter, for example. Now, whether you can discern the difference, that's a different story, but you have that whole range. Because it's just a sliding instrument, it can actually be any expansion that you want. Okay, so there you go, and that's why why the trombone has that great range in pitch. It's because it technically has an infinite number of column lengths. All right, next we want to look at the flute. Now the flute, a little bit more of a, I guess you'd call it, so a standard instrument, so to speak. So here's my mouthpiece down here. All right, now what does the flute have? The flute has a series of holes on top of it. So I'm going to add a series of holes on top. And of course it has the flange at the end there. So how does this work? Well, the musician, and again, I can't hear you laughing, but the musician can cover up the holes. So these are supposed to be fingers. And you can laugh all you want. So the fingers cover the holes. So I'm going to have two scenarios there for you. So what happens in this first one, you blow into it, all the holes are covered. So that means that you would get, you'd use the entire column, so you kind of get that fundamental wavelength and look like that. All right, so all the holes are covered. What happens then in the second situation where I open up a hole? So here are the holes. Now I'm only covering two holes up. So I've lifted the third finger up, kind of like British tea, pinky out. I don't know. I'm trying. There we go. So I've lifted my finger. What happens now is we've essentially shortened the air column. Oops, put my flange on here. Okay, or the bell. We've shortened it. So it's like that air column there has been, or that length has been eliminated, because now the standing wave goes to the open hole. So we've shortened the wave, and that's where that delta L comes in. So you shorten the wave, so that means that you are, if you shorten the wave, shorten our column here, that means we've increased our pitch. So if the person playing the flute can increase the pitch. So when holes are open and closed, and closed, the sound wave has a length to the first open hole. All right, that's how your flute and whatever other instruments kind of fall into that category. All right, I'm going to cut this video off here. I want to talk about the guitar, some of the factors that affect the guitar, and then I got two quick examples that I'll run through with you. All right, so we'll see you in the next video.